this video is about the development of quantum theory, specifically about how scientists took the results of the flame test and other experiments that were done with the light emitted by atoms and figured out how the electrons are set up inside of atoms from that. So after this video, you should be able to explain why different elements emit different colors of light and lines of light based on an explanation of what is going on with the electrons inside of atoms. All right, the first thing I'd like to point out is that light is a spectrum of colors. White light sent through a prism is going to make a rainbow. And it'll make pretty much every color if you start with an incandescent light bulb. If you start with a fluorescent light bulb, it'll actually only make certain colors. It's kind of a neat thing. It's one of the reasons that fluorescent light bulbs are energy efficient. They trick our eyes into thinking that they're white, but they're actually only certain colors of the rainbow. But if you send light from certain elements glowing inside a tube, or in a flame test through a prism or a diffraction grating, you get this. So hydrogen, it's kind of hard to see, but actually is making four distinct colors here. The four colors that it's making are violet, blue violet, teal, or you call it blue green. That's a G, green and red. So hydrogen actually only makes four visible colors of light that we can see, and only very distinct colors there. Helium makes a lot more. It makes a lot more colors. Lithium makes a lot. Neon makes a heck of a lot. Notice when we look at neon lights, like in a pizza place window with our eyes, we see orange, but there's actually a little blue in there and a little bit of green too. But there's a lot of orange and red and yellow, and it all blends together in our eyeballs to look kind of red-orange. That's what our brain sees. Sodium lamps are street lamps. They kind of look orangey. It's because they make a very bright orange line here, but there actually are a few other colors in sodium. And potassium makes a bunch of colors too. One thing to point out is, what the heck's causing these lines? All these elements, you heat them up and you get these lines after you put it through a prism. This was a question that pretty much scientists at the beginning of the 1800s had a really tough time with. So they observed that you got thin lines of one color instead of all colors. Each element makes a different pattern in color. Hydrogen has few lines, other elements have more. It's almost like a fingerprint for an element. And the conclusion that they made was that electrons are releasing the light, and they must be able to have only certain energies. It's important that you know something about light first. This is a light spectrum of visible light. That the top there, violet, has a short wavelength and has a high energy and a high frequency. Whereas at the bottom, red has a longer wavelength and has a lower frequency and lower amount of energy. All right, so this is how it works. You take an atom, so let's say this is a sodium atom that you put inside a flame, and you give it energy. Energy can come in the form of light or heat or electricity. Glow-in-the-dark stars work when you shine light on something and it glows. So it's doing the same thing by light. Heat, you can heat it up inside a light bulb or a Bunsen burner flame. Electricity, you can zap it inside a light bulb and it'll do the same thing. So this is the atom. The electron right here absorbs the light and it bounces up an energy level. So it goes up here. But this process, by the way, is called atomic excitation. Electrons don't like to be up in high energy levels, though. They want to be as far down as they can get. And so what happens is the electron wants to go down. This is a picture of the second step of this process. And when it goes down, it has to get rid of energies. It's in a higher energy level because it absorbed energy. It can't destroy the energy, so it's got to get rid of the energy. How's it going to do it? It's going to release a little packet of light called a photon. And that's what we end up seeing. We see the energy. Now, you'll notice that there are rings in these pictures. It ends up that the distance that it drops, that distance lines up very specifically with a color of light. And so what happens is different elements have different colors of light emitted because the spacing between their energy levels is different. It's unique in every element. All right. Energy level is the exact amount of energy that an electron and atom can contain. It's not actually a ring. That's a really important point. Closest to nucleus has the lowest energy. But here's what you do need to know. Bigger drops mean higher energy. Lower drops mean less energy. And remember, violet is a more energetic form of light than red. Okay, the ground state's when the electron is in the lowest possible energy level. It can't drop anymore. Excitations, when it absorbs energy, goes to a higher energy level. That's called an excited state. A key thing is don't say the electron gets hotter or faster. The electrons don't really have temperature. They don't really have the same thing as speed, so don't use those vocabulary words when you describe this process. Just say it gets energy. Absorbing energy is enough to say. And then finally, it gets rid of the energy when it emits light. All right, so this is a picture of these energy level things, and all of the light from hydrogen or any element is caused by the electrons bouncing around between these energy levels. Specifically, they bounce up when they absorb energy, and then when they emit energy, when they emit light, they go down again. Hydrogen's a nice, easy picture, though, because we actually know the energy levels in hydrogen really well, and they're like this. So let's say the electron starts off its life in the first energy level and goes up to the sixth. It absorbs energy in like a heat or light or some other kind of energy it absorbs. All right, if it's up there in the sixth energy level and it's bouncing around the sixth energy level, all right, it wants to drop down. If it happens to drop down to the second energy level, it has to give off light. It gives off violet light. Well, let's say it absorbs some more energy. So you put it in a flame and it goes up to the fourth energy level. And let's say it drops down to the second again. It has to give off blue-green light. That distance happens to line up very well with blue-green. Right? Let's say it drops back down to the first. It actually gives off a kind of light we can't see called ultraviolet light, UV. That's the kind of light that gives skin cancer. In other words, you probably could use a hydrogen bulb as a tanning bed. I wouldn't recommend it, though. Skin cancer isn't so much fun. So let's say the electron now down in the first energy level absorbs energy again, pops up to 5, and then drops again to 2. It's going to give off blue-violet light. And then pops up to 3, goes down to 2. It's going to give off red light. That 3 to 2 process is red light. And it can just pretty much bounce around between the energy levels here. And every time it goes down, it emits light, and every time it goes up, it absorbs energy in the form of light, heat, or electricity. Right. So again, those transitions, the electron falling the way it does, which is kind of hidden a little bit beneath my arrows here, but those transitions are actually caused by those electrons falling causes the light to be made. Right. I'd like to point out that, again, that anything higher than anything down to the first energy level will cause UV light. So 2, 3, 4, 5, whatever energy level will cause UV. And anything to 3, 4, or 5, like smaller jumps at the top, will cause infrared light. That's another kind of light we can't see. That's a lower energy form of light. All right. Now, this is a different topic. You might already have this in your notes, but you probably don't. This is the development of the quantum theory and the 4 scientists who kind of fleshed out this whole picture and really said how electrons are moving around inside atoms. First thing you need to know is the Heisenberg uncertainty principle. It ends up that we were drawing on the last few slides electrons as little dots in those rings. They're not really dots. They're really waves. De Broglie said that electrons act as waves. So since an electron is a wave, well, what part of a wave is the wave? You can't say that part's the wave, or that part's the wave, or that part's the wave. It's really the whole thing that's the wave. And since the whole thing's the wave, the electron is spread out all around the atom all at one time. It's not in one little spot circling around the nucleus. All right, that leads to the Heisenberg uncertainty principle. You can't really know where the electron is. And if you do look for it and it happens to be in one specific place, you don't know where it's going to go. You can't know both the position and the velocity with 100% certainty. It's called the uncertainty principle. It's just kind of one of the laws of the universe. It's kind of crazy. If you want to do some Googling on it, you'll get all sorts of crazy results that happen to be really true. It's one of those really fun parts of science where not even the scientists who do all the work really know what's going on completely. Right, you do need to know that the electrons move randomly. That's really what they're doing. They're moving all around the atom. We don't really know where they are. According to the laws of probability, it means they might be someplace. They might be someplace else. We don't really know 100%. We're probably sure that they're close to the nucleus. Niels Bohr came up with the next one. He's the one who made those atom models with rings. He didn't really think they were rings, by the way. He just drew them that way. Their energy levels, they're the energy that the electron can have. He made them by knowing that electrons were acting as waves. And the neat thing was that his model of hydrogen happened to give those lines of light that hydrogen makes really, really well. So his model worked really successfully for hydrogen. Unfortunately, it didn't work when you put more than one electron in the atom, which is why Schrodinger came along and came up with the last model of the atom. This is the modern model of the atom. We have Schrodinger to thank for that. What he did was he pretty much said, okay, all these electrons are waves, and they're all moving three-dimensionally around the atom. And the waves are, since they're moving in 3 dimensions and they're all repelling each other and we don't really know what they are, it's kind of like just a big fuzzball. And he was very successful writing the math equations for coming up with this big fuzzball. So really the most accurate picture of an atom is just a big fuzzball because the waves of the atom are all going around. You know, I know you just really like my picture of the atom here. So that's kind of our best picture that we can draw of an atom. Now we know how the electrons are moving inside, but it doesn't really lend itself to pictures that well. All right, so in summary, atoms emit light only of certain colors and not others. They make those lines, the line spectra. This is unlike a light bulb, which makes all the colors. It's caused by electrons falling between energy levels. Remember, they absorb energy to go up, but when they emit energy, they go down. And the difference between the energy levels, the height of the drop, corresponds to the color of light that they make. Bohr is the guy who showed that this happens by falling energy levels. So he made the models of the atom. He made these drawings with energy levels in them. And the energy levels exist because atoms are waves. And Schrodinger created the modern quantum mechanical model of the electron cloud of the atom, saying, okay, the electrons are going to follow these wave equations, and we know what the equations are, and pretty much it's just a big fuzzball. But we can actually go and we can examine how the electrons work because of Schrodinger's equations. Thank you for watching this video.